Welcome back, and today we'll be covering chapters on forecasting, chapter 12, as part of our discussion on operations management. And in this lecture, we will look at strategic role of forecasting in supply chain and operations management, and look at forecasting time horizon, then look into qualitative versus quantitative forecasts. Then in terms of the actual forecasting demand, look at the components of that, and specifically focusing on the time series methods, and then finally address the issue of forecast accuracy. In terms of forecasting, the definition is a process of predicting a future event. So forecasting focuses on trying to take an educated guess about an event that is going to happen in the future. And in context of operations management, more importantly, how much the demand is going to be so that we are ready for the supply and prepare our operation processes to be ready for that. And in this case, besides the production, you have looking at inventory, personnel, how many people do you need to have? Do you have enough people to make the products or offer services? Or the facilities associated with that. Do we need more warehouse space? Do we need more production space? So those will be the type of issues that will come under or will be addressed as part of forecasting results. Forecasting time horizons indicate how far in the future do we typically forecast. And in this case, it could be a short-range forecast, which is daily all the way up to 1 year. And generally, these type of forecasts are about less than 3 months. These encompass focus on the immediate future and focuses on purchasing parts or raw material, job scheduling of the people, workforce level in the near term as to do we have enough people to tide us over for the next quarter, etc. Job assignments, who will be doing what, and on what machine, where, in which location, and production levels of various products that the company offers. In terms of medium range forecast, that can go all the way up to 2 years, and these focus on sales and production planning, which will be a topic that will be discussed in later chapters, and budgeting issues that come in. And then we have the long-range forecast, which focuses on, it typically encompasses a period longer than 2 years and focuses on new production planning of new products, facility location, if we need to move our facility from one location to another location, or what type of projects that we need to undertake for R&D. Distinguishing features in this case is medium and long-range forecasts deal with more comprehensive issues and support management decisions regarding planning and products, plant and processes. So we are looking at much more of a strategic nature of decision-making that where forecast helps us in. Whereas short-range forecast usually employs different methodologies than long-term forecasting, and over here, what you're looking at is operational decisions that you. So short-term forecasts, given the nature of it, since we are looking at immediate future, tend to be more accurate than long-term forecasts in this case. Now, in terms of what is the importance of forecasting, even if it's an educated guess nevertheless, influence on the product life cycle, because from introduction and growth requires longer forecast than maturity and decline, because at maturity and decline, you pretty much have figured out the kinks in the product as well as know the markets in this case. So there is much more, competition is pretty well defined and it's already established. Customers know the product and are more likely to offer stable demand environment. In terms of as the product process through the life cycle, forecasts are useful in projecting the staffing levels, inventory levels, factory capacity issues in this case. Typically, the type of forecast you have is the economic forecast, which address the business cycle, inflation rate, money supply, housing starts, etc. And then technological forecasts, which focus on predict rate of technological progress or development of new products that are coming down the pipe. And also look at demand forecasts, which predict sales of existing product, which tends to be the focus of our discussion. Strategic importance of forecasting. Human resources can use that to make decisions on hiring, training, laying off workers, if the long or medium-term forecast indicate that the need for the product is not as much. Capacity-wise, capacity shortage can result in undependable delivery, loss of customers, and loss of market share. So forecasting is important so that we are not having huge inequalities between demand and supply. And then, of course, in supply chain management, it does make sense to have good supply relation by not fluctuating too much in the orders that are placed in to the supplier, so that they can also try to look at regulate their own production environment. The effects of inaccurate forecasting, and in this case you can see how if the producer underproduces, which leads to inventory shortages, which in this case will affect the demand. We have late delivery, stock outs, and shortage cost, high shipping cost. Whereas, and that typically happens if the forecaster under forecasts. So your supply is less than demand. Whereas on the other scenario, if you over forecast, you end up, factories end up overproducing excessive inventory. And in that case, you have spoilage because the product expiry date comes up, and even though the product is not sold, obsolescence, some new products come in and your products become antiquated, waste, high inventory cost, etc. So all those lead to inequalities between supply and demand in this case. So now let's look at the two different types of forecasts. First, we'll focus on the qualitative forecasts, where no numbers are needed, or this typically is used where situation is vague and little data exists. So typically for new products, that's where we'll use this. New products and new technologies is where such forecasts are used. Management, marketing, purchasing, engineering are sources of internal qualitative forecast in this regard. This is based on intuition, experience, management judgment, knowledge, expertise, and opinion of to predict future demand. So all these tend to be opinions or based on somebody's own experience. So forecasting sales on the internet is an excellent example, because if there is no previous data that exists for a company, they just have to kind of go with expert opinion. So in this case, jury of executive opinion, which is pool's opinion of high-level executives, sometimes augmented by statistical model, but most cases it's still an opinion. Delphi method is also used extensively in qualitative forecasts, which involves soliciting forecast about technical advances from panels of experts, and then these are queried iteratively as again and again and again till we have some sort of consensus building going on. Salesforce composite is another way of arriving at a qualitative forecast, which is estimates from individual salespersons are reviewed for reasonableness and then aggregated, composited together. And then you have consumer market survey, ask the customer as to what they think, will they buy this product in the coming year or coming month, etc. Now let's talk about the quantitative forecasts. And quantitative forecasting is used when situations are stable and historical data exists. So typically this is used for existing products and current technology, very different from the qualitative forecast that we typically mentioned earlier. This is based on data statistics, involve mathematical techniques. So for example, forecasting sales of color televisions, which is something company has been making in the past, has the data, knows what has been in the sales in the past. It makes more sense to use quantitative approaches to predict future sales in this case. So methods of forecasting, in this case, for quantitative approach, are naive approach, which is just eyeballing the numbers, if you will, as to what we did last time. And formal time series method is statistical techniques that use historical demand data to predict future demands and focus on systematically reducing forecasting errors. In this case, so those are the ones that we'll look at, along with moving averages, exponential smoothing, trend projections that are listed in here. And then you have causal models, associative models, which is example of that is linear regression, attempt to develop a mathematical relationship between demand and factors that cause its behavior. That's something typically students cover in quantitative business analysis course in this case. And patterns of demand, in this case, you can demand can depend on time frame. How long is the time frame that you're selecting? What type of demand behavior is exhibited by this product customers? And what are the causes for such behavior? It's a new product, or it's a well-established product, the newness or the excitement, buzz around it, versus it's a run-of-the-mill staple item, if you will. So those will all dictate the patterns. Various patterns that exist in here, we start with horizontal, which is steady state demand. Data tends to move sideways, that is, demand hovers around a certain number in this case. And then you have trend, which is a gradual up, long-term up or down movement that you have of demand, and changes due to population, technology, age, and cultures. A typical several-year duration that you tend to see. Then you have seasonal patterns. An up and down repetitive movement in demand occurs periodically, usually within a year. So as a year has 4 seasons, or in this case, if you think of quarter, there are 4 quarters. So you can see quarterly seasonality or monthly seasonality, end of the month. People do not spend money on conspicuous consumption, or they tend to save money so that they can somehow manage to survive the month. And as soon as the paycheck comes in, there is much more of superfluous consumption that happens. So that could be. And seasonality in a week, which are 52 weeks in a year, typically would be, there will be much more of absenteeism that will be seen at the end of the week or the start of the week, either Monday or Friday, as compared to middle of the week, as an example. Then in a day, whether it's in a week or a month, you can see there could be, in this particular case, how the various consumption of electricity in a household, which probably will be, if you think in terms of at the start of the day, the electricity consumption goes up, and then as people leave for work or school, or kids go to school, the electricity consumption drops down, and then once again, that will go up when people come back home in this case. So those are all examples of a variety of seasons that one can see in this case. Then you have cyclical pattern, which is up and down repetitive movement in demand, but this takes multiple years to exhibit itself. So typically it could be based on business cycle, political, economic factors that may be involved, job market situation, etc. Random variations, movement in demand that do not follow any pattern. So if you think, if you want to look at visually, you can see components of forecasting demand. You have the random variations, small squiggly lines that do not follow any pattern. And then you have the seasonal peaks. Every year, within a year, you can see it has a consistent pattern that is being repeated. And over time, how there is a trend component that is going up, and then the actual horizontal average demand over 4 years, that's the horizontal component. It hovers around a certain area that can be seen. And but if you see some sort of pattern that presents itself over several years, that's a cyclical pattern that will be shown in this case. Now, in terms of specific forms of forecast movement, just to separate out things, you can see the random movement over here, whereas a seasonal pattern is every so often that you have this trend, and then when this trend is shown over this pattern is shown over a larger time frame, that's the cycles, the business cycle, and this is where economy was going good for several years over here, and then it started going down for a few years, and then it started going up again. And those are the type of things, waxing and waning, that may happen. And then this is the trend with seasonal pattern that is being shown in this case. Now, in terms of forecasting and supply chain management, accurate forecasting determines inventory level in the supply chain. Typically, we use that in continuous replenishment. Supplier and customer share continuous updated data, as we mentioned in the supply chain discussion. Typically managed by the supplier, reduces inventory for the company, and speeds customer delivery. Variation of continuous replenishment is quick response, which is used in apparel industry in US and throughout the world. And just in time, which is used for predictable demand environment products, where emphasis is on reducing the inventory, or almost eliminating excess inventory. And vendor management inventory is let the vendor carry the inventory on the behalf of the manufacturer, and manufacturer will ask to, it's still owned by vendor till the manufacturer uses it on the shop floor. And then stockless inventory is actually not carrying any inventory at all. A variation of that is the just-in-time, other is make-to-order type of products, if you will. And then you have quality management. Accurately forecasting customer demand is a key to providing good quality and service. So one of the key things that, and also it is helpful in strategic planning. Successful strategic planning requires accurate forecasts for future products and markets. So in this case, if you look at the forecasting process, first step is to identify the purpose of the forecast. Then one goes about, assuming we are doing a quantitative forecast, then we collect the historical data accordingly, plot the data to identify any patterns, if we see some seasonality or cyclicality or any trend component in there. Select the forecast model that seems most appropriate for this data, and then in this case develop and compute forecast for the data. Check the forecast. If the accuracy of the forecast is acceptable, if not, then you select another model until we are happy with the forecast accuracy. And if once that's done, forecast over the planning horizon, adjust the forecast based on additional qualitative information and monitor the result. And then and keep on fine-tuning to improve the forecast accuracy in this case. Now in terms of time series, this is the assumptions of the time series model are, there is information about the past that is available. This information can be quantified in the form of data, and the patterns of the past will continue in the future. So those are the things that one has to assume in order to make sure time series data can be used for forecasting purposes. In terms of relate to forecast, in this case, the x-axis, the independent variable is time, as contrast to causal models where it could be anything else. But when you use time, you look at the sales over time or any other dependent variable over time, that's time series models that are being used. So in here, we'll be looking at moving averages, both simple moving average as well as the weighted moving average. We'll look at exponential smoothing as well as the linear trend line examples. Now in terms of moving averages, we have the naive forecast example, which is demand of the current period is used as the next period forecast. So that is, in order to say how much should we stock for tomorrow depends on how much we sold today. So that's a naive way of doing it, but still, nevertheless, it is, for a lack of any other better forecasting model, one that can be used as a starting point. simple moving averages uses average demand for a fixed sequence or period and stable demand with no pronounced behavior pattern. That's one of the key assumptions that we have. And weighted moving average, in contrast, we are using weights that are assigned to more recent data. So we end up weighing more recent data, higher weight as compared to the less recent data. So in terms of naive approach, let's look at that. If you think of the orders that we have for the a given year by monthly number of orders per month. So in this case, you can see January has 120 orders. So if that is the number, the forecast for February would be 120. And now, there won't be any forecast for January because we didn't have the data for previous December. So in this case, that cannot be forecasted unless you have the previous December's data. So for February, so we forecast, we carry 120 items, but then we realize only 90 were sold. So next time, we tend to carry, our forecast will be that we'll sell 90. So that's a naive way of approach of doing the forecast, but nevertheless, that at least as a student of forecasting, you need to be aware of that. Let's look at simple moving average, and the word simple means it's a straightforward average, and the moving part is something we'll explain in the context of an example. But in this particular case, what you're looking at is moving average is sum total of all the demands divided by n, and so that's the average that you have. And in this case, every single demand that you've taken has been equal weight, and that's the simple part of it, simple average. Okay? And in this particular case, what you're looking at is the average of n previous demand data, and if you can see how the formula arrives at, note that n past observations are equally weighted. And in this case, they're equal weight, and that's where that's the word simple means. Issue with moving average forecast, all n past observations are treated equally. Observations older than n are not included at all. So that's one of the downsides of simple moving average. It requires that n past observations be retained in here. And problem when thousands of items are being forecasted, then you end up losing the data richness because of excluding items from the which are older than n past data points. Now you notice that we are taking the same yearly data, and in this case, month. The orders are given for each month, but since it's a 3-month simple moving average, we are unable to calculate the moving average for the first 3 months because there's no prior data that is available for them. So in order to calculate the first possible month for which we can calculate our 3-month simple moving average will be the month of April, because for the month of April is the first time when you have 3 previous month data available to you. For the month of April, this 103 is calculated from 120 plus 90 plus 100 and averaged out. And once you take these 3, add them up, divide by 3, you'll come up with 103. For the month of November, what you need is take the most recent 3 months, which is August, September, and October. So you have 90 plus 110 plus 130, and those are the numbers in this case that are shown over here. That is 90 plus 110 plus 130, and average of that, once you divide by 3, you get a 110. So that becomes a simple moving average for the month of November in this case, as a way to calculate that. Now, in terms of the same thing can be done to calculate a 5-month moving average, but notice that earliest possible month, if we are calculating a 5-month moving average, we'll lose the data for the 5 months, and the earliest we can calculate is the forecast will be the month of June, because we don't have the previous data, in order to calculate these moving averages for 5 months prior to that. So in this case, the month of November will take October, September, August, July, and June. So 90 plus 110 plus 130 plus 75 plus 150 plus 50, all divided by 5, which will give you 91. So in this case, notice the difference is how many periods are you taking to calculate the moving average. The longer the number of periods, the more smoother the demand is going to be, or forecast is going to be, because it's not going to fluctuate that much. And here is an example where actual is indicated by the line that is almost blue in color, whereas the pink line over here is the 3-month data, which is less wavy, and the least wavy, most smooth line is the 5-month. If you were to take 6-month or 7-month or 8-month, you'll notice that will become even much more flatter as the variability is reduced as the longer time frame you take into account in your forecasting. Now let's go ahead and look at the weighted moving average. And in this case, rather than for a simple moving average of 3-month, each month, previous month was weighted as 1/3, 1/3, 1/3. Or for a 5-month moving average, each month was weighted as 1/5, 1/5, 1/5, 1/5, 1/5, which is 20% each. Over here, these weights are different for each month, and still they add up to 100%, and they all add up to 1 in this case. So for example, if you were to take, we need to calculate the November forecast, but remember the data that is given to us is 90, 110, and 130, but now we are using a model where we are using a weighted forecast, and we are putting 50% weight on October, 33% weight on September, and 17% weight on August instead of 33, 33, 33. And in that case, you have the 0.5 of 90, 0.33 of 110, and 0.17 of 130. And once you calculate the sum product, you come up with 103.4, which is different from what you calculated earlier. Now, exponential smoothing, the next topic of exponential smoothing, this is averaging method that includes all past observations. So this is actually superior to simple moving or weighted moving average forecast because of the fact that it does not throw away the actual order data. So all the data is kept in there. So that's one of the definitely advantages. Widely used, and it's more accurate. Reacts to more recent changes and weights recent observation much more heavily than the older observation. So the weights are between alpha, the weights are between 0 and 1. And so you notice that today's observation, the most recent data is weighted at alpha. The next most recent is weighted at alpha times 1 minus alpha, and then keep going in the past, and all the way till the very first possible data that you had. So given this information, you can see the forecast for the future period t plus 1 equals to alpha, which is the weight of the period t, which is the previous period, times alpha times 1 minus alpha of ft plus 1, ft, and then ft plus 1, and all the way. So this all, the second portion all simplifies to just this information. And in that case, so the new forecast becomes a weighted sum of old forecast and the actual demand. So in this case, all you need is only 2 values, dt and ft, that are required to compare with and moving averages. Because in case if you're taking a 12-month simple moving average, you need 12 past data. Over here, that's not the case. All you need is 2 data points. The last period's actual demand and the last period's forecast. That's all you need to calculate exponential smoothing. So this alpha parameter, the weight is determined empirically, whatever works best. Rule of thumb is alpha has to be less than 0.5 And that is the way to to actually have used for most staple items. Alpha of 0.2 or 0.3 works well in many cases. But in industries where fashion trends are very fleeting, higher alphas seem to work better. So it all depends on what type of industry you're working in. So given this, that's the formula of ft plus 1 is alpha dt plus 1 minus alpha ft. And in this case, all the taxonomy of what that means is given to you. ft plus 1 is forecast of the next period. Demand and forecast dt and ft are the actual demand of the present period, previously determined forecast of the present period. And alpha, as I mentioned earlier, is the weighted factor, the constant. So in this case here, let's look at an example. So alpha is between 0 and 1. If alpha is 0.20, then ft plus 1 becomes 0.20 dt plus 0.80 ft. Whereas f is 0, then what you're saying is my forecast is going to remain constant. What I'm going to forecast for future period is same as what my forecast was for the last period, which was the same as the forecast for the previous period before that. So forecast does not reflect recent data at all. If alpha equals to 1, then you cancel out the ft, so your forecast of the future period becomes just the dt, what was the demand of the present period, which basically is the naive forecast that we covered earlier. So those are the simplifications, if you can check. And now, in this case, taking our own same example of the 12-month yearly data of orders, and in this case, the demands are given to you. So if alpha is given to you as 0.3, if you decide to use alpha of 0.3, you can easily calculate the information. Now, in this case, one of the things you'll notice that in order to calculate F2, we still need F1, which is the demand for forecasting, a forecast for period 1. If it's not available, you just assume that to be 37. So 37 and 37 is being used over here. So demand dt is 37, and forecast that is being put in here is the 37. So your February forecast ends up being 37 because 0.3 of 37 and 0.7 of 37 add 0.3 and 0.7, which is 1 of 37. 1 times 37 is 37. And then for March, and that's where you'll see some changes happening. Now you're using 0.3 of 40 and 0.7 of what the forecast of F2 is, which is 37. And this sum product comes out to be 37.9. And then you continue doing this all the way down. So we have to calculate every single forecast in order to calculate the forecast for the month of December. So in this case, that comes out to be 51.79. So in this particular case, you can notice those are the numbers that are coming in for alpha of 0.3 that I just explained to you all the way till 51.79. So that's the forecast for the month of January, the next January that you have. And in this case, if you were to use alpha of 0.5, you get a slightly different number. So one can easily compare and contrast which of these forecasts is more accurate. We'll talk about that a bit later. But in terms of exponential smoothing, notice that alpha of 0.3 really indicates that any new fluctuation does not vary our forecast that much. So you'll see much more stable forecast doesn't veer too much. Actual is given with the blue line, and as alpha is increased, you'll notice that it also will become sensitive to any recent changes in actual demand data. So alpha 0.5 is much more wavy as compared to alpha 0.3. Now let's talk about the linear trend line. And in this case, fitting a trend line to historical data points to project into the medium or to long range. Linear trend can be found using the least square technique. So in this case, you have the formula of YA plus BX, which is the typical slope line, straight line. A is the intercept, y-intercept, and B is the slope of the line, and X is the time period, and Y becomes the forecast for that time period. So you're using a straight line to a trend line to fit the data. So in this case, B can be calculated using the formula, B and A can be calculated using these formulas in this case. And X bar and Y bar are the mean of X values and Y values. So here are the formulas that are indicated. And using those formulas can easily provide you with the least square example. And in this case, you have the X period, the Y, and from that you can calculate XY. And also you can take the squares of the first column to come up with X squared. So you need these two, the last two columns are needed to use it over here, use the information in here. And you can see the sum product of XY and X bar. So in this case, those are the numbers that you're looking at. And moving on to X bar is 6.5, which can be calculated, which is take 78 divided by 12, which is number is 78, and divide by 12. And then you have Y bar, which is 557, and divide that by 12 is 46.42. And then you have sigma XY, which is right here. Sigma XY is 3867 minus then 12 times the 6.5 that was calculated earlier and 46.42 that is calculated over here. And sigma X squared, which is summation of X squared that was calculated in the last column, 650. And subtract from that, subtract 12 times 6.5 raised to power 2. And once you do this calculation, it comes out, B comes out to be 1.72. Plugging that in here, you come up with Y bar minus B times X bar and come up with the A intercept, which is 35.2. Notice that that is the straight line. So even though this is the actual data, this is the linear trend line that best fits the data in this particular case. And that is the genesis for regression model down the road, but we'll just limit ourselves to discussion of linear trend line. Now, let's talk about the seasonal adjustment, which is typically repetitive increase and decrease in demand, which happens due to seasonality, so one has to adjust for that seasonality. So use seasonal factor to adjust forecast. In this case, seasonal factor can be calculated by SI for a particular period is the demand for that period divided by sum total of all the demand. So let's look at an example of that. And in that case, notice that we have 3 different year worth of data. Demand is in thousands for each quarter. So the first quarter, you're looking at 12,600 units of demand. That's what the number indicates. So accordingly, the demand is given to you, and these are given by quarter. These are first quarters of the years 2003, year 2003 and year 2004. And then similarly, second quarter for those 3 respective years, quarter 3 for each of those years, quarter 4 of each of those years. When you total them up, that comes out to be 42, 29.5, 21.9, 55, and then those are the final totals. So in this case, in order to look at demand 1, you are looking at a seasonality of the first quarter. You take, this is the sum total of all the demand. And in this case, that goes in the denominator, and then 42, which is sum total of all the quarter 1 demand, goes in the numerator. So 42 divided by 148.7 is 28%. If there was no seasonality, you should expect the demand by quarter should not vary. That means each quarter should have about 25% demand. But in this case, notice that quarter 1 actually has 28%, so a little bit higher demand, whereas quarter 2 tends to have to only 20% demand. Quarter 3 has only 15% demand, and quarter 4 has 37% demand. So notice that demand actually does fluctuate by seasons in this particular data. So that adjustment has to be made accordingly in the model that we use. So here is the seasonal adjustment. For example, for year 2005, if we were to use the linear trend line for, in this case, y is 40.97 plus 4.3x. So in that case, you plug in 4, which is the fourth year, and you get 58.17. And in this case, for the first quarter, so that is the base demand by the quarter, but in this case, for the whole year, 28% of that occurs in quarter 1. So 28% of 58.17, that means 16.28 or 16,280 units of is forecasted in terms of sales, sales forecast that is you're looking at. And then you have in season 2 is much less of 11.63, and then 8.73, and then finally 21.53. So one can accordingly plan their production in this case. Forecasting accuracy that we look at, in this case, the focus is on trying to figure out how good is the forecast. And in this case, we can look at several of these measures. Mean forecast error, MFE or bias, which is measures average deviation of forecast from the actual data. Then you have mean absolute deviation, which measures the average absolute deviation of forecast from actuals. Mean absolute percentage deviation, MAPD or MAPE, mean absolute percent error. This measures mean absolute deviation as a percentage of forecast. And then one can easily calculate standard squared error, which is used in regression or variance calculation. And then tracking signal, measure how well the forecast is predicting actual values. Now, in terms of MFE or bias, is sum of all the difference, the true forecast error, actual minus forecast will give you the deviation, whether it's positive or negative. And taking that cumulative number and dividing by n will give you the mean number in this case. So you want MFE to be as close to 0 as possible, minimum bias. A large positive MFE means that forecast is undershooting and the actual observation, and a large negative MFE will represent you are over forecasting in this case. So that tells you how accurate you are in this case. But 0 MFE does not imply the forecast is perfect. It just means it's on target. Because some of the positives may be canceling out the negatives in this case. So one has to watch out for that. To remedy that situation, that's where MAD is used, because we only look at the absolute value of forecast error. So absolute deviation is being looked at, which is actual minus forecast, the deviation, and take out the sign by just putting the absolute numbers, and summation of all that divided by n. So this measures the absolute error. So positives and negatives do not cancel out as with MFE. So in this case, you do want MAD to be as small as possible, because any larger number, the larger the number, the more deviation it is recording. So, but there is no way to know if MAD error is large or small in relation to actual data. And that's where you need to use, let's go ahead and do a calculation on MFE and MAD. So for example, MFE is, as I mentioned, the notation wise, you have summation of dt minus ft divided by n. So whereas MAD is absolute value of dt minus ft divided by n of the summation of that. So in that case, you have t is the period number, and dtft is given to you, and then the vertical lines are the absolute value. So here, in this particular case, you can see how these numbers are calculated. So MFE and MAD calculations. So you can see for each period, they're given the demand, and for exponential smoothing of alpha of 0.3, you can calculate the forecasts, and one can easily calculate the error or percentage, the deviation of the forecast from the demand. So in this case, these are the actual deviations, positive and negative, and on this side, you're removing the sign, and just if this negative 0.2 becomes just 0.2. So some of the negatives did cancel out with the positive, so you have 49.31 over here as a result, whereas this is 53.39 when you just only look at the absolute numbers. Now, this is 11th month data because, and in that case, since there are only 11 data months that can be forecasted, notice that we lose the first one in this case. So in this case, MFE comes out to be 49.31 divided by 11, and that 49.31 is coming from here. And in this case, that comes out to be 4.48, whereas the mean absolute deviation is 53.39, which is the sum of the last column right here, and that is comes out to be 4.85. Now, notice one of the things that we mentioned earlier is the fact that there's no way to know if MAD error is large or small in relation to the actual data. So in that case, one has to look at several other factors, other measures for forecasting accuracy. So one of the ways to actually see if the number MAD that is providing is that meaningful or not is to look at in a relative basis. So MAPD is basically taking the forecast error, absolute forecast error on as a percentage of actuals. So in this case, this is provide the same information as MAD except measures deviation as a percentage of actual data in that case. And then MSE is another forecasting accuracy measure which takes the forecast errors, square them, and then take a summation of that, and divide by n, measures the square forecast error, which is the error variance. Square root of error variance is the standard deviation that we all know about. This recognizes that large errors are disproportionately more expensive than smaller errors, but it's not very easy to interpret as compared to MAD, MAPE because of its non-intuitive nature of it. Then tracking signal is basically calculate how well the forecast is predicting actual values. In this case, you have the ratio of running sum of forecast errors divided by mean absolute deviation. Good tracking signal has low values, and the forecast is continually high or low. The forecast has a bias error in this case. So let's see the calculations in this scenario. So you have the mean absolute percentage deviation, the formulas, and let's see how that play out. So you can see in terms of the numbers that are provided to you, in this case, that exponential smoothing of 0.3 gives you MAD of 4.85, but MAPD of 9.6% when you take on a percentage of actual error that we calculate. A linear trend line also we calculated in this case. So one can compare these data points. Forecasting control, so the tracking signal, as I mentioned earlier, monitors the forecast to see if it's biased higher or low. So one MAD is approximately 0.8 standard deviation. So control limit of 2 to 5 MADs are used most frequently. So in this case, you notice that that's the formula that we mentioned. And tracking signal values, in this case, you are take the demand and the forecast is calculated, and the error is subtraction of 40 minus 37 will give you 3 as an example. And in this case, summation, this is a running sum of forecast error. This is 0, that's 0. 0 plus 3 is 3. 0 plus 3 plus 3.1 is 6.1. That's a running sum of forecast error. So that's what we are doing. So then 3 plus 3.1, which is 6.1, minus 1.83 becomes 4.27. Then add to this whole number 4.27 plus 6.72 is 10.99, and keep going So everything added till this point becomes this number over here. So that's the running sum of forecast error. So you have those, and for each of these, you can calculate the MAD and then divide the running sum of forecast error by MAD. So 3 over 3 is 1, 6.1 divided by 3.05 is 2. So you can see what the tracking signal looks like. The average number comes out to be 2. So anytime you are over that number, you notice that your bias is coming in. We are way, slowly increasing from, what the level of 2 is, and now going 3, 4, 5, 6, 7, 8, 9, 10. So the tracking signal is indicating we are actually going totally out of whack in this case. So that may not be a good model to use. So in this case, one can easily track the plot. So you can see exponential smoothing of alpha of 0.3 is not a good idea, whereas if you were to do the same calculations for linear trend line, that seems to be within the range. So that pretty much wraps up our discussion for forecasting chapter. We'll see you again when we discuss another topic in operations management area. Take care.